Okay, welcome. My name is Mr. Pileggi. I am going to be your calc teacher this semester. We're going to cover chapter 1. That's just basically a pre-calculus review. And so this chapter is not required for you to send me your completed notes, but it would be probably good for you to watch through these videos and maybe jot some notes down on your sheet, just to get the rust out. This is C3PO. He will be holding the markers for me. Me and my son build some life-size droids, and so you'll know you're on my video when you see him standing in the corner as my assistant. All right, so section 1, we're looking at functions and graphs. So it says find the intercepts of y equals x minus 1 and x minus 3. So they already have it factored for us. And so when we're going to find the intercepts for this, what we're going to do to find the x-intercept, you're going to set y equal to 0. And so when y equals 0, we go back up to the factored quadratic here. And remember the rule with 0. Anytime you multiply by 0, you get 0. But also, if you get 0 through multiplication, the only way that can happen is if one of these is 0. So you just simply set this by nominal equal to 0, and this one equal to 0, and then solve. So x equals 1 and x equals 3. So we have our x-intercepts. It's 1, 0, and 3, 0. We're not done though, because they didn't specify just find the x-intercepts. They said find the intercepts. So now what we're going to do is we're going to set x equal to 0. And that will determine our y-intercept. So everywhere where I see an x, I'm going to insert a 0. And then now remember, 0 minus 1, that's just negative 1. 0 minus 3 is negative 3. Negative times a negative is a positive. And so we're looking at 0, 3 for that. Now, if we were going to graph this, it would be a parabola that was facing up. It's a quadratic equation. But now we have these points. We could use these points to do a sketch and say, all right, well, it crosses the x-axis at 1 and 3. It crosses the y-axis at 3. And if we know it's a parabola, we can kind of say, well, I know the vertex is somewhere down here. So this would just be a sketch. We'd have to actually find the actual vertex if we wanted it to be a more accurate graph. But that is finding the intercepts. Now, what if they give us a more complicated problem and tell us to find the intercepts? Then, if I erase it too fast, remember, you can just scan back and pause and get everything written down that way. So xy equals 4. Again, we're going to set y equal to 0 to find the x-intercept. But when we do that, we end up with x times 0, which equals 4. And that says 0 equals 4. And 0 does not equal 4. So that is no solution, which means there is no x-intercept. All right, and we set x equal to 0 to find the y-intercept, and the exact same thing is going to happen. We got 0 times anything is 0, so we end up with 0 times is equal to 4, and that's not true, so no solution and no y-intercept. And so that would be The graph of that one would be kind of weird, right? We had xy equals 4 as our graph. We end up with like one of these with vertical asymptotes, horizontal asymptotes. And so no intercepts in that. All right. Okay, moving along. We have the x-axis symmetry, the y-axis symmetry. So if it's symmetric about the x-axis, if it's symmetric about the y-axis, or if it's symmetric about the origin. The way to check that algebraically is to see if it's symmetric about the x-axis. What you do is you replace y with negative y. And then if you end up with the same equation, then it's symmetric. Same equation that you started with. All right. Y-axis symmetry, you replace x with negative x. And again, it's symmetric if you end up with what you started with. Same symmetric if equation is the same as the original. All right, and then symmetric about the origin, you do kind of both. You replace y with negative y and x with negative x. And then if you end up with the same equation that you started with, it's symmetric about the origin. So same equation means symmetric about the origin. All right. So what would that look like if we ran a test on this one? If we have y equals x to the fourth minus x squared plus 3, and we want to check to see algebraically if these are symmetric. So for x-axis symmetry, what we do is we replace the y with a negative y. So I'm replacing this with negative y, and that's not going to be the same, because now I could multiply both sides by negative 1, and I end up with y is equal to negative x to the fourth plus x squared minus 3. That is not the same as this. It is the opposite. And so it's not symmetric about x. All right. To see if it's symmetric about the y-axis, so y-axis symmetry, what we're going to do is we're going to replace all of the x's with a negative x. So y stays the same. I put in a negative x where that was. It's still to the fourth. Minus a negative x, and then it's squared, and then plus 3. Now, when I simplify this, this is negative x times negative x times negative x times negative x. That ends up as positive x to the fourth. Same thing happens with the x squared, and then plus 3. We end up with the exact same thing that we started with. So this is symmetric about the y-axis. All right. Then to check to see if we have symmetry about the origin, we would flip both of them. So basically, I'm going to take origin symmetry. We're going to take and replace this with negative y and these with negative x. And you probably already know what's going to happen here, right? Because this, we already just did it, set is the same, but this is going to flip the sign. So we're going to end up back with that equation, which is not the same as what we started with. Therefore, this is not symmetric about the origin. All right. Okay, let's take a look at sketch the graphs of the following. So sketching a graph means that we're not going to find points. We're not going to build a table. We're not going to use some graphing program or something. What we want to do is just kind of do a quick sketch and get things in approximately the right spot. All right, so for the first one, we have 4x minus 2y equals 6. So this one, we're going to isolate the y. We'll solve for y. And divide everything by -2. We're solving it out for y, so we have y equals mx plus b. Remember, 2x minus 3. So the slope is 2 over 1. The starting point on the y-axis is -3. That's why it's called slope-intercept form. And so we just go down to -3, put our starting point from that point. This is the rate of change. +2 means up 2. +1 on the bottom means to the right one. So up 2 and over 1, we put another dot and then just put that in there. We're not building a table. We're not finding 4 points and plotting x and y and all that. Just doing a quick sketch. So that was linear, or creates a line. Y equals 3 minus x squared. That is a quadratic equation. And that is going to be a parabola. So for parabolas, we're going to use a parent graph. A parent graph is kind of a general idea of what a parabola looks like. It's got a vertex of 0, 0, and then just going up. So that's the general idea of what it's supposed to look like. Now, they did some stuff here. We got y is equal to -x squared plus 3. This plus 3 shifts it up 3 units. And the negative in front of the x squared reflects it over the x-axis. So reflection over x. All right, so we go up 1, 2, 3. And then it's, instead of opening up, now it's going to open down. And that's going to be our graph. Then the next one is an absolute value graph. So that just looks like a V. And again, we have a parent graph. So the parent graph of this one is just got a slope of 1, up 1 over 1 from 0, 0, and then the reflection over the y-axis is the same thing. The -1, 1, those would be the points. So what we're going to do with this is going to shift it. The +3 shifts it up 3. And the -2 actually shifts it to the right 2. I know that's kind of opposite of what you'd probably think. You would think, oh, that would shift it to the left, but when it's inside of the absolute values, it actually shifts it to the right. It might be easier to think of this point. What would zero this out? A 2 would zero that out. And when that is 0, that's gone, and then y is 3. So 2, 3 is this point right here. 1, 2, 1, 2, 3. And so there's our point. So we're just picking this graph up and plopping it down in this spot instead of at the origin, 0, 0. All right. So that is page 1. Let's see what we got. Oof, there's a couple of pages. So we'll do 2 pages, and then I'll cut it, and we'll do the next 2 pages on the next video. All right. So we're still looking at functions and graphs, section 1, chapter 1. This is a pre-calculus review. And so let's see, find the points of intersection algebraically. And so they give us 2 curves that they want us to find the points of intersection at. And so what we're going to do here is pick the easiest thing to solve for. So in this case, y. Y is super easy to solve for. We just add it over to that side and get y equals x minus 1. And we add x squared to both sides of the equation. We get x squared minus 7. And so now what we're going to do is we're going to set this equal to that. We're just y equals y. And so we have x minus 1 is equal to x squared minus 7. Oh boy, so now it looks like we're going to get to bust out our sweet factoring skills. We want to isolate because it's a second degree and a first degree in there. We're getting it all over to one side and then equal to 0. And so now we're going to factor and solve. So that means multiply. This has a 1. Leading coefficient is 1. So we're just multiplying what multiplies to be -6, but adds up to be -1. And that might just pop into your head. But if you're a little rusty, we could look at all of the possibilities: -1 and 6, -6 and 1, -2 and 3, -3 and 2. Only integers. We only want integers when we're factoring. So we end up with -3 and 2 is the winner. That adds up to 5, -5, +1, close but no cigar, and -1. So this is what it factors into, but our actual answers end up being the opposite. It would be what makes this 0 and what makes that 0. So x minus 3 has to equal 0, or x plus 2 has to equal 0, and then we're isolating the variable. And so when you're finding it, they wanted the points of intersection. Right now we've only found the x values. So we have to find the point. Now, you can put it back in here or I can put it back in there. But I need the y value that matches with this x value. So y is equal to 3 minus 1. That's the easier one to do. 2. 3 comma 2. For you doubting Thomases, or doubting Tamikas, you would end up with the same thing. 9, I put in 3 there. 3 squared is 9. 9 minus 7 is 2. So it wasn't vastly more difficult, but this one is definitely easier to sub in. So this, we end up with -2 minus 1, and y is -3. So -2, -3 is the point of intersection for that one. Let me make sure everybody can see the video. Okay, good, good, good. All right, so 2 points of intersection. That's what they wanted. That's what they got. Quick review on what the domain and the range is. The domain is a list of what x can be. The range is a list of what y shakes out to be. And so when we're looking at domain and range, domain is the set of all real numbers for which the equation is defined. So we're kind of the set of all real numbers. That's excluding the imaginary or complex number system. So all real numbers for which the equation is defined. Now, a lot of times your domain is just all real numbers, negative infinity to infinity. The range is the corresponding y values that go with those x values. In layman's terms, you would just say what x can be, what y can be. And so here, i.e., sometimes you'll see i.e. i.e. just means, in other words, all images of x denoted as f of x when they're talking function notation. F of x, remember, is just kind of a fancy way of saying y. All right, so remember here, let's jump into g of x is equal to 6 over x. All right, so this would have a limitation on it because you have a variable in the denominator. And remember, it's undefined if you try to divide by 0. You can never divide by 0, ever. So I have to solve this for 0 to find my restrictions, my domain restrictions. And so they just want find the domain, and then it says if you're worried about the range, then we'll look at the graph. And so we're not graphing these right now, so we're just going to look at the domain for the rest of page 2 here. So 6 over x, x equals 0 is where it's going to crash, because if I put 0 in there, I'm taking 6 divided by 0, and 6 divided by 0 is undefined. And so we can't have that. So this is our restriction. X cannot be equal to 0. So the way we note that, we say the domain goes from negative infinity to 0, and then we put a parenthesis on it. That means not including the 0, in union with a parenthesis, which it doesn't include the 0. So 0 isn't in this set, to positive infinity. I know that's kind of a weird way to say it because you're naming 0, negative infinity to 0 and then 0 to positive infinity. But because there's not a bracket on it, this excludes 0. It would be all reals except for 0. And that is called interval notation. That is what we're going to use. That's what we use in calculus, interval notation. So you don't just write out all reals except for 0. We notate it as an interval. All right, let's see. G of x is equal to x plus 3 over x squared minus x minus 6. Now, when we're worried about the domain, which is what we're worried about, we don't really care about the numerator. We're just focused on the denominator. This cannot be 0. This might look very familiar because we just factored that one a minute ago. X minus 3, x plus 2, right? Multiplies to be negative 6, adds up to be negative 1. So we're looking at 3 and we're looking at negative 2. Those are the two values that are not allowed, because if I put in a 3, 3 squared is 9, minus 3, minus 6, that's 9 minus 9, that's 0. And now I'm dividing by 0. I cannot do that. Same with negative 2. That shakes out to be 0 if I put in a negative 2 there. So what we have to do for the domain here, and a lot of times you'll see just a capital D and then the colon. So the domain here is going to be from negative infinity up to negative 2, not inclusive. And then it's going to go from negative 2 to 3, not inclusive, no brackets here. And then 3 to positive infinity. And so that would be our domain, our set. If we looked at that on number line, if you wanted to go kind of old school, what that would be is here's 0, negative 2, here's 1, 2, 3. And we would want everything except for, we'd want to hold out negative 2, and we'd want to hold out positive 3. But the domain would be everything else. So it would be all of this and all of these and all of this. And now remember, that's an infinite. These are all infinite sets. It's negative infinity to negative 2. But even from negative 2 to 3, you might think, oh, that's finite. But really it's not, because we didn't limit any of the, we could have irrational numbers in there. We could have 1.1, 1.11, 1.111, 1.1111, 1.111. You know, we could go infinitely small in between those sets. So that's why it's important that we use this interval notation instead of, you know, just saying except for. So negative infinity to negative 2, that's what this signifies. Negative 2 to positive 3, that's that. And then 3 to positive infinity, that's that. And this is what it would have looked like back in your number line days with open and closed circles and such. All right, let's look at the other two here. And then we'll go to the next one. So we've got f of x is equal to 1 over the absolute value of x plus 5. Interesting. Okay, so remember how we do this. We have the absolute value of x plus 5 is equal to 0. And so normally we would split this. Because 0, it's absolute. The only way that you can get that is if there's a 0 inside there. So spoiler alert, it's going to be negative 5, and that's it. But remember how we do absolute value problems. If this was something other than, if this was a positive number, we'd have two solutions to get there. So we'll still go through the motions here. You write it out just as it is, and then we do the opposite of it. Without that's not the absolute value, that's just parentheses. So either, you know, what would make that equal to 0, negative 5, and then you do the distributive property here, and then what would make that equal to 0, and it's also negative 5. So the only way to get a 0 in the denominator there is if you insert a negative 5. And so the domain is from negative infinity to negative 5, not inclusive, and then negative 5 to positive infinity. All right. And the last one on this page. Now, again, remember we define the domain as the set of all real numbers. And so there are complex numbers. I can take the square root of negative 25 and call it 25i squared. But that's pushing it into the complex number system. We're trying to keep it into the real number system. So we're going to look at this problem as greater than or equal to 0. I want this inside to be greater than or equal to 0, because 0 is okay. I can take the square root of 0. I can take the square root of a positive, but as soon as I take square roots of negative, an even root to a negative, then I'm looking at the complex number system, and we're trying to keep it into the real number system here. So what do we do here? Let's see. We got a couple of rules. We'll isolate our variable. Remember, when you divide by a negative 1, that will change the inequality sign. We got x squared, but now it's less than or equal to 25. And now we want the square root of that. So we do the square root. Oh, you know what? I should have moved the x squared over. That would have been easier. Oh, well. And remember, the plus or minus is going to happen here because we could do a positive or a negative in on that. And so we end up with plus or minus x is less than or equal to 5. So that's going to split it into two problems. Here, I'm going to just pull it up here. So x is less than or equal to 5, or negative x is less than or equal to 5. So x is less than or equal to 5, that's done. But here I'm going to divide by a negative 1 again. And now I got x is greater than or equal to -5. So what does that mean? Well, that gives me an actual interval. If I look at this on a number line, we have 0 here, we got -5 over here, we got +5 over there. It is everything greater than -5, so that's going closed circle and or bracket. Let's use what we use in calc instead of the closed circle and open circle stuff here. Let's use our calculus notation. We don't use open and closed circles anymore. You use brackets. So bracket means closed circle. And then, so greater than -5 is going this way, less than 5 is going that way, and both of them are restricted. So it's that and that. Actually, I said or. That's actually going to be an and. All right. And so, what does that look like in interval notation? Just pretty much like what we have right there. -5 to +5 with brackets on either side. All right. So that is chapter 1, the pre-calculus review, page 1 and 2.